A mathematical mystery that changed everything. Imagine I told you there's a mathematical rule so simple that it seems obviously true. But if you accept it, suddenly there are line segments with no length, and you can magically turn one sphere into two identical spheres without adding anything to it. Welcome to one of mathematics' greatest paradoxes, the axiom of choice. For over 100 years, mathematics has been built on this seemingly innocent principle, yet it creates results so bizarre they seem impossible. Today, I'm going to take you on a journey through this mathematical mystery that nearly destroyed one brilliant mathematician's career and split the mathematical community in half. Let me start with a simple challenge. Choose a number. You might pick 37 or 42, but that's your human brain at work, not mathematics. In math, you can't truly pick things randomly because formulas always give the same result. This is why computers don't have true random number generators. They use algorithms based on your current time to create numbers that appear random. So if we can't pick randomly in mathematics, how do we select anything? The only way is to follow a rule. We could say, always choose the smallest thing. For positive integers, that's easy. It's 1. For prime numbers, it's 2. But what about real numbers? Any number. Positive, negative, whole, fraction, or irrational like pi. Try to choose the smallest real number. It's impossible. They stretch to negative infinity. Even if we try choose the smallest number after 1, we're stuck. There's 1.01, then 1.001, then 1.0001, comma, and so on forever. What number truly comes after 1? This mission to resolve the problem of mathematical choice began with one man in 1870, Georg Cantor, a German mathematician, who took on the seemingly impossible task of putting real numbers in definitive order, and it nearly killed him. Cantor made a revolutionary discovery about infinity itself. For centuries, since Galileo's work in 1638, mathematicians believed all infinities were the same size. Galileo showed that there are exactly as many square numbers as natural numbers by matching each natural number with its square in a one-to-one mapping. But Cantor wasn't satisfied. In 1874, he wondered, what if there were infinities of different sizes? He set out to compare natural numbers with real numbers between 0 and 1 using his famous diagonalization proof. Cantor assumed he could map these sets perfectly, writing an infinite list, matching each natural number with a real number. Then he created a new real number by taking the first digit of the first number and adding 1, the second digit of the second number and adding 1, and so on. This new number couldn't be anywhere on his list. It differed from every listed number by at least 1 digit. This proved something remarkable. Some infinities are bigger than others. The real numbers form an uncountable infinity, larger than the countable infinity of natural numbers. Cantor's success spurred him toward an even grander goal, proving that every set, even uncountably infinite ones, could be arranged in what he called a well order, a definitive sequence, where every subset has a clear starting point. He could well order the integers by starting at 0, then going 1, minus 1, 2, minus 2, ranking them by distance from 0. But the real numbers? That seemed impossible without a clear starting point, despite having no mathematical proof. Cantor published his well-ordering theorem, claiming every set could be well-ordered. His confidence came from an unusual source, his deep Lutheran faith. He believed God was speaking through him, saying his theory stands as firm as a rock. The mathematical community attacked him viciously. His former teacher, Leopold Kronecker, called him a scientific charlatan and blocked his applications to prestigious universities. The rejection drove Cantor to multiple nervous breakdowns and confinement in sanitariums. The vindication Cantor desperately needed came from an unexpected source. In 1904, at an international mathematics congress, Professor Julius Koenig announced proof that Cantor's theorem was wrong. Cantor sat humiliated in the audience with his family, but also in attendance was Ernst Zermelo, a German mathematician fascinated by Cantor's work. Within 24 hours, Zermelo found the fatal flaw in Koenig's proof. Within a month, he published proof that every set can be well-ordered, and it was flawless. Zermelo's breakthrough came from recognizing something Cantor had been using unconsciously: the assumption that you could make infinitely many choices simultaneously from any set, including uncountably infinite ones. This needed to be formalized as a new mathematical axiom, the axiom of choice. The axiom states that if you have infinitely many non-empty sets, there's a way to choose one element from each set simultaneously. We can't say how we're choosing or which elements we've chosen. The axiom just guarantees that such choices are possible. Using this axiom, Zermelo could well order the real numbers by repeatedly choosing numbers from the remaining set, labeling them x1, x2, x3, and so on, extending beyond the natural numbers to omega, omega plus 1, omega plus 2, until every real number was ordered. But accepting the axiom of choice came with a price: disturbing paradoxes that shattered mathematical intuition. Giuseppe Vitali used the axiom to create sets with no measurable length. Stefan Banach and Alfred Tarski proved you could split a solid ball into 5 pieces and reassemble them into 2 identical balls, then repeat this process infinitely, creating unlimited balls from one. These results seem impossible, but they're mathematically valid. The catch? The pieces you create are non-measurable. They have no consistent definition of size, length, or area. The mathematical community was in crisis for over 30 years. Some called these results obviously false, others obviously true. In 1938, Kurt Gödel proved there's a mathematical universe where the axiom of choice holds alongside other accepted axioms. In 1963, Paul Cohen proved there's also a universe where it doesn't hold. Like the parallel postulate in geometry, the axiom of choice is independent, neither provable nor disprovable from other axioms. It's a choice about what mathematical universe you want to work in. Today, the axiom of choice is almost universally accepted despite its paradoxes. It makes mathematics more powerful and elegant, reducing 20-page proofs to half a page. As one mathematician put it, without the axiom of choice, you're working with both hands tied behind your back. The question was never whether the axiom of choice is right, but whether it's right for what you want to do. Sometimes, the most counterintuitive ideas unlock the deepest truths about the mathematical universe we inhabit.